Let's introduce Gay-Lussac's law.
Gay-Lussac law, named after French chemist Joseph-Louis Gay-Lussac, described the relationship between the pressure and temperature of a gas at a constant volume. States that the pressure of a gas is directly proportional to its temperature, provided it remains constant. The mathematical expression of Gay-Lussac law can be written as proportional T, P over T equals K, where P is pressure exerted by the gas, T is absolute temperature of the gas, and K is a constant.
The relationship between the pressure and absolute temperature of a given mass of gas can be illustrated graphically as follows. Gay-Lussac's law implies that the ratio of the initial pressure and the temperature is equal to the ratio of the final pressure and temperature for a gas of fixed mass kept at a constant volume. This formula can be expressed as follows. P over T1 is equal to P over T2, where P1 is the initial pressure, T1 is the initial pressure, P2 is the final pressure, T2 is the final temperature. Gay-Lussac's law states that at constant temperature and pressure, the ratio of volumes of gases involved in a chemical reaction is always in simple whole numbers. In other words, the volumes of gases in a reaction can be expressed as a ratio of small integers.
This law is based on the observation that gases combine or react in simple and definite proportions by volume. For example, when hydrogen gas reacts with oxygen gas to form water vapor, the volume ratio is 2:1. This means that every 2 volumes of hydrogen gas, 1 volume of oxygen gas is consumed, and 2 volumes of water vapor are produced.
Gay-Lussac's law is a consequence of the ideal gas law, which describes the behavior of gases under various conditions. It is important in understanding stoichiometry, the study of the quantitative relationship between reactants and products in chemical reactions. It is worth noting that Gay-Lussac's law applies only to gases and under conditions of constant temperature and pressure. Any changes in temperature or pressure can affect the validity of this law.
Let's understand this law better. Let's conduct the bicycle pump experiment. In this experiment, we will use a bicycle pump, a pressure gauge, and a container to observe the relationship between pressure and temperature.
We will start by setting up the apparatus. Attach the pressure gauge to the tire's valve system and ensure it is securely connected. Make sure the tire has a fixed volume. Now, let's begin the experiment. We will measure the initial pressure of the gas inside the tire using the pressure gauge. This will serve as our starting point. Next, we will use the car pump to pump air into the tire. As we pump air, the temperature inside the tire will increase due to the compression of the gas. At regular intervals, we will measure the pressure inside the container using the pressure gauge. We will record these pressure readings accurately. As we continue pumping air into the container, we will notice that the pressure increases. This is because the increased temperature causes the gas molecules to move faster and collide with the container walls more frequently, resulting in an increase in pressure. In summary, the car tire pump experiment demonstrates Gay-Lussac's law. As we increase the temperature by pumping air into the tire, the pressure inside the tire also increases.
Understanding Gay-Lussac's law is crucial in various real-life applications. For example, it helps us understand the behavior of gases in engines, where the combustion of fuels increases the temperature and pressure, resulting in the movement of pistons and generation of mechanical energy.
Additionally, Gay-Lussac's law is essential in refrigeration systems where compressing a gas increases its temperature, allowing for effective cooling. That concludes our video tutorial on Gay-Lussac's law using the car tire experiment.
Here are some examples of computation using Gay-Lussac's law. A cylinder of gas has a pressure of 5.40 atmosphere at 25 degrees Celsius. At what temperature in Celsius will it reach a pressure of 6.50 atmosphere? We must convert the Celsius into Kelvin by using the formula K is equal to C plus 273.15. The initial temperature is equal to 25 degrees Celsius plus 273.15 is equal to 298.15 Kelvin. First, we must identify the given. The P1 is 4.40 atmosphere, T2 is 25 degrees Celsius is now 298.15 Kelvin, and P2 is 6.50 atmosphere. We need to solve for T2. We can use the formula P1 over T1 is equal to P2 over T2. Cross multiply and divide both by P1, so we can cancel the P1 on the other side and T2 will remain. T2 is equal to P2 multiplied by T1 divided by P1. Now, we can change the formula into numbers. The solution is T2 is equal to 6.50 atmosphere multiplied by 298.15 Kelvin divided by 4.40 atmosphere. Cancel the atmosphere. T2 is equal to 440 Kelvin. Since the final temperature is in Kelvin and based on the question, we must find its Celsius form. We must convert it into Kelvin by using the formula C is equal to K minus 273.15. C is 440K minus 273.15 is equal to 167 degrees Celsius. Now, the final temperature is 167 degrees Celsius.
A gas has a pressure of 103 kilopascals at 25 degrees Celsius. What will be the pressure when the temperature reaches 928 degrees Celsius? First, we must identify the given. The P1 is 103 kilopascals. T1 is 25 degrees Celsius to 298.15 Kelvin. And T2 is 928 degrees Celsius to 1201.15 Kelvin. We must solve for the P2, but first we must convert the Celsius in Kelvin by using the formula K equal C plus 273.15. T1 is equals to 25 degrees Celsius plus 273.15 is equals to 298.15 Kelvin. T2 is 928 degrees Celsius plus 273.15 is equals to 1201.15 Kelvin. We can use the formula P1 and T1 is equals to P2 and T2. Cross multiply and divide both by T1 so that we can cancel the T1 on the other side and P2 will remain. P2 is equals to P1 multiplied by T2 divided by T1. Now we can change the formula into numbers. The solution is P2 is equals to 103 kilopascals multiplied to 1201.15 Kelvin divided by 298.15 Kelvin. Cancel the K. P2 is equals to 415 kilopascal.
Example number 3. A gas has its temperature decreased from 760 torr to 320 torr at 225 K. What was the initial temperature of the gas? First, let's identify the given. The P1 is 760 torr, the P2 is 320 torr, and the T2 is 225 K. You must solve for T1. We must use the formula P1 over T1 is equal to P2 over T2. Cross multiply and divide both by P2 so we can cancel the P2 on the other side and T1 will remain. T1 is equal to P1 multiplied by T2 divided by P2. Now, we can change the formula into numbers. The solution is T1 is equal to 760 torr multiplied by 225K divided by 320 torr. Cancel the torr. Therefore, T1 is equal to 534K.
That's it. We hope you found it informative and helpful. If you have any questions or comments, please feel free to leave them below. Thank you for watching and keep exploring the fascinating world of science.